So first I want to let you know, so this week's lab will be a 2-week lab. I'm going to change the deadline to the week after next week. Okay. So inverter is very easy to implement on the FPGA. Just use how to do it. Simulation very simple. You can see that demonstrate the following combinational logic blocks in both simulation and on the board. So switches, LEDs, inverter, it just use a switch, one of the switches as the input of the inverter, and LEDs, one of the LEDs as the output. 2-bit flatter, when I was looking at examples from 2 years ago, students submitted 1-bit flatter instead of 2-bit. So the 1-bit flatter adds 2 bits, so that's why it's confusing. And they're thinking, all right, a 1-bit FA is a 2-bit FA. Actually, it's not. So the FA has AB, CI, CL, and S. So they're thinking you are adding 2 bits together, so this is a 2-bit flatter. That's wrong. So 2-bit flatter is different. Okay, just keep in mind. You need two of these FAs. Here's A0. So it is literally adding up B1, B0 to A1, A0. And it's giving you S0, S1, C out. Okay. So it's adding A1 to A0 to B0 and adding A1 to B1. So for each FA, I have A0 here. So what is the other one? Yeah. And here's CI. That's C out from the first one, and CI to the second one. And eventually it has a CO, and these are the S1, S0 of the output. When you're writing, coding it up in Verilog, you can create one FA first and then put them together in your test bench. Okay, so eventually the chip is going to have a CI here, and you have to short it here, and definitely has A0, B0, okay, and A1, B1 to make the connections, and CO S1, S0, and this is the 2-bit S. So this becomes S1, this becomes S0, right? To make the connections here as well. So in the test bench, this is actually A0. It's a 2-bit A bus. Okay, like that. So you need to code up your FA module first. A single bit FA first. Oh, sorry. 1 bit FA, and it has A, B, CI, S, CO. Input, output. Is that correct? So that's a 1-bit full adder. That's one single FA here. And you can directly write a test bench below it, but don't forget this. It's also a test bench. So just do this. So let's declare the variables later. But now how do we make the connections? I'm going to just show you the connections. So I'm trying to create a test bench, and I'm going to place 2 of them in here. So definitely the test bench is going to have A, so 2-bit A and B. Keep in mind, when you declare it, keep the bracket in the front. When you are assigning values, they are behind the variable. So A, B, CI, A, B, CI, and you have to do these as well. And so S and CO, these are just the wires. And the thing is, you need a little connection, little wire here as well to connect the 2 FAs. So I'm going to just name this guy as CX. Okay, so I'm going to declare that wire here. Okay, then I'm going to instantiate these submodules in the test bench. So what's the name of it? 1-bit FA. So I'm going to do UUT1. So that's the first one. First one. So which is being shorted to where? CI is to CI, no problem. See? A is shorted to A0. B is shorted to B0. S is shorted to S0. Anything else? Yeah, CO is being shorted to CX. And done for the first instantiation. Then instantiate another one, UUT2, just make the connections very similar to this one, to do this. And then write a for loop. So you can combine, because when you are doing the simulation, how many inputs do you have? So you are trying to explore all the combinations of the inputs. So it's actually 1, 2, 3, 4, 5. 5 bits as the input. So it's very difficult to list all the possibilities in initial begin, right? You assign values to each one and incrementing by 1 until 2 to the 5th power. So use a for loop instead of listing every single combination. How do we use a for loop to do it? For I equals to 0, I less than, so we have 5 bits, 2 to the 5th, which is 32. I equals to I plus 1. And begin, end. How to do it? You force these bits into one binary number. So it becomes B1, A1, B0. I don't want to do that. So just do this, B, A, C, I. Okay, B, A, C, I. It's just 5 bits. Doesn't matter which one you want to flip first. 5 bits, 2 to the 5th number of combinations. It's going to explore all the possible inputs. Use a curly bracket. However, if this is an initial begin and end here, and you need to assign initial values for all these things. So just to give B a B, these are more than one bit, right? So it's 1, 0. Five bits, 2 bits here, 2 bits here, 1 bit here. And initial begin, you can assign initial values to it. That's why you need register types for these guys. They are assigning initial values to them. That's why in the very beginning, I have regs for these guys. And that's the main part of the script for this 2-bit FA. And run the simulation first, show the demonstration in the simulation, and eventually implement this onto the FPGA board. So the question here is how to do it. So two switches, so 5 switches and 3 LEDs. That's how you do it on FPGA. A input AND, very simple. 4 to 1 mux. So this is just letting you learn this conditional statement. It's a little bit different from other languages. So this is the mux, right? And why is this the mux? 4 to 1 mux? No, not. Okay, so why is this 4 to 1 mux? So what is a 4 to 1 mux? So 4-to-1 multiplexer. A device has 4 inputs. And you can make the selections to choose which input should be sent to the output 1. So how many inputs do you have? 4. So how many selection bits do you need? 2. Because only 2 bits can give you 4 different selections, different options. Okay. So on FPGA, how do we implement it? How to demonstrate it? You don't have to explore all the possibilities. Okay. So for example, these inputs are switches. Okay. So these 4. So for example, you use 6 switches, and these 4 are the 4 inputs. You can turn on which one you like, doesn't matter, but you want to explore at least like 2 to 3 possibilities. And the bottom 2 switches are the selection bits. So you can, if you turn both of them off, it's going to give a 0, 0 to the selection bits. So it should pick up A, so it should send A to Y. And then you can try to turn it on, turn it off. I mean for A, the corresponding switch of A, turn it on, turn it off, see if it's being sent to the single LED. That's LED 0. See if it is able to send A to Y, and do the same thing for all the other bits. So the conditional statement in Verilog looks like that. S1 question mark, is S1 1? Then get into here. If S1 is 0, get into here. It's a recursive conditional statement. If S1 is 1 and S0 is 1, then do this, select this one. If S1 is 1 and S0 is 0, select the D2. You know what I mean? So it's a question mark and colon. So the colon separates the 2 options. And the colon is making a conditional statement work. So it's asking if S1 is 1. If S1 is 1, pick up the first one, the left side of the column. If S1 is 0, select the second one, the right-hand side of the column. And inside is still the same structure. If S0 is 1, select D3. If S0 is 0, select D2. So in that way, there are totally 4 different possibilities. 0, 0, 0, 1, 1, 0, 1, 1. Okay, so it is able to select corresponding digital lines and assign them to Y. So you just need a one statement to form the entire logic of the 4-to-1 mux. Very convenient. You don't have to code it up. You don't have to draw all the gate level circuits and make connections. It takes time. This only 5 seconds. Running LED. I provided most part of the code. And it turns out that the reset function didn't work really well in the morning, and I highly recommend you not using the reset function, just delete this part. But you can make it work, which is great. I just don't have time to find out the correct version of it. So the input here is definitely clock, right? Clock, reset, LED, 4 LEDs. So demonstration here is showing you that LED is being shifted to the left. and then come back to the right. The first one on the right hand side, just running through the 4 bits. And the frequency is 1 Hertz. How to make that work? There's a clock, physical clock actually. It's physical on the board. It's 100 megahertz. So the crystal oscillator is going to provide a 100 megahertz clock physically. And so that's why you want to count this one to 100 megatimes to make a change. That's how you can get a 1 Hertz output. So in 1 second, the physical clock is going to oscillate for 100 megatimes during 1 second. So only you are going to count it, right? Count. Whenever the rising edge comes, you count by 1. So during the 1 second time period, there are totally 100 mega rising edges. So you count for 100 mega rising edges, then do something. So that action becomes a 1 Hertz action. So obviously, here is a shifting of the LED. So this must be when the counter reaches that, I'm going to shift it, and I want to make the shift to be 1 Hertz. So what is this count? Should be 100 mega. If it's not reaching 100 mega yet, I'm going to keep incrementing counter. It's going to be a count plus 1. Okay. I just do nothing. Just assign whatever the LED is to the current state. It's not changing anything. Seven-segment display. One more time. It's a common cathode. No, common anode, I'm sorry. So see, all the anodes of the LEDs are being shorted together to one point. It's common anode. So we need to give a 0 to the pin in order to turn on that corresponding LED. Okay, so which changes the numbers in this lookup table. So this is forming a lookup table. It's using a case statement. I have to look at the input from the switch. So you are using the switch to give an input to the 77 display. So you have 15 switches, and whatever the binary number you can form on the switches is going to display on the 77 display. So that's the idea of that task. Okay. So to connect the switch to the input number, which is it's called digit over here. That's it for everyone, every single task for the lab. Any questions for the tasks in the tutorial? So here provides an example of the for loop. Right? You can refer to this one. This is in the combinational block tutorial this week. The parity generator and checker, which are here. So this is due next week, right? Next Thursday. Yeah. And you are supposed to make the report for the data types tutorial available by the end of today, if you haven't. And this is due next Thursday, so it's not a problem to worry about for now. Maybe tomorrow after the lab. So you should focus on the lab for today. Okay. Hopefully you can finish most of them today, and you'll still have time to wrap it up next week. Okay. So I have 2 lab sessions. I'm going to change the deadline here to the week after next week. Any other questions?